Hello everybody, so in this video we're going to begin with Chapter 11, Integral Calculus. And your learning objectives for the chapter are the following. You're going to do integration as anti-differentiation of functions. You are going to learn how to calculate and apply definite integrals. We're going to do finding area under curves, meaning between the curve and the x-axis, and also areas between two different curves or functions. We're going to learn about anti-differentiation with a boundary condition. We're going to learn how to solve kinematic problems involving displacement s, velocity v, acceleration a, and total distance traveled. Working with integration of polynomial functions, trigonometric functions and their inverses, as well as exponential functions. And finally, we're going to do integration by inspection or reverse chain rule, and integration by substitution. So we're going to work specifically on part 11.1, antiderivative. So an antiderivative of the function lowercase f of x is a function uppercase f of x such that the derivative of uppercase f of x is equal to lowercase f of x wherever f of x is defined. So basically what they're saying here is the antiderivative is the opposite process of the derivative, as we're going to see in the next slide with a few examples. So here we can see the uppercase f of x, and if we differentiate that, we get lowercase f of x. And if we do the anti-differentiation of lowercase f of x, as we can see here, we will get uppercase f of x. So basically that's the relationship between a derivative and its integral, which is another word for anti-differentiation. So to the left, we have table 11.1 with examples of functions paired to antiderivatives. So if the function f of x is 1, the antiderivative will be x. Well, obviously, because if we do the derivative of x, we would get 1. The antiderivative of x is x squared over 2, because if we do the derivative of this, we would get x, and so forth, right? We also have the case of sine of x. The derivative of sine of x is cosine of x. Therefore, the antiderivative of cosine of x is sine of x. If we have cosine of 2x, the antiderivative would be 1/2 sine of 2x. With Euler's number, because Euler's number to the x, if you do the derivative of that, it's going to be Euler's number to the x. Therefore, the opposite is also true. The integration of e to the x will be e to the x. With sine of x, the integration or the antiderivative is going to be negative cosine of x. Why? Because if you do the derivative of negative cosine of x, you're going to get sine of x. So here we are on example 11.1, and it says, given the function f of x is equal to 3x squared, find an antiderivative of f of x. So notice that the word an implies that there can be more than one antiderivative of f of x. So why is that? Well, look, if we have 3 times x squared, how do we find the antiderivative of this? So before, when we wanted to find the derivative, we would multiply by the exponent and then subtract 1 from the exponent. For the antiderivative, in the cases of x squared to something or x to the power of something, what you do is that you add 1 to the exponent and then divide by that same new exponent. In this case, 2 plus 1. So what we're going to get here is 3 times x to the 3 over 3. And then this cancels out, and we get x to the power of 3. But why does it say find an antiderivative? Well, because we could have had the case where the antiderivative would be something like x cubed plus any constant. So you could have plus pi, or you could have the case where the antiderivative was x cubed minus 1, right? And notice that the derivative of any of these would give us 3x squared. So in the next slide, you're going to find a few examples of notation for integration. So if the derivative of x cubed is 3x squared, the integration of, notice the symbol, right? You have this symbol here, which is an S actually, of 3x squared dx is going to be x cubed plus c, where c means any constant, right? C just represents any constant that could possibly be there, as we saw in the previous examples. We know that the derivative of the square root of x is equal to 1 over 2 times square root of x. That means then that the integration of 1 over 2 square root of x dx is going to be square root of x plus c. We know that the derivative of tangent of t is secant squared of t. Therefore, the integration of secant squared of t dt is going to be tangent of t plus c. And this is another case where if you have the derivative of v to the power of 3/2, that is going to equal 3/2 times v to the 1/2. That means then that the integration of 3/2 v to the power of 1/2 dv would equal v to the power of 3/2 plus a constant c. So again, remember that the integration is simply the opposite of the derivative or the antiderivative. So next we have example 11.12. But before we do that, let's look at a couple of rules for differentiation and integration. So it says to the right here, suppose that f of x and g of x are differentiable functions and k is a constant. Then a constant factor can be moved through an integral sign. That is, if you have the integration of k times f of x dx, you can rewrite that as being equal to k times the integration of f of x. Also, an antiderivative of a sum or difference is the sum or difference of the antiderivatives. So basically what that means is that if you have a case where you have, say, the integration of f of x plus or minus g of x dx, you can separate that into two different integrals. So now we're ready to do example 11.2. So notice that in the first case, they want us to evaluate the integral of 3 cosine of x dx. So this is the first case where you have a constant factor that can be moved through the integral sign. So this is the same as saying 3 times the integral of cosine of x dx. But we know what the antiderivative of cosine is. It's going to be just sine of x. So this is going to be 3 times sine of x, and don't forget plus a constant c. Case B says integrate x cubed plus x squared dx. So this would be the second case where we can separate the antiderivative into two separate antiderivatives, right? So we can rewrite this as the integration of x cubed dx plus the integration of x squared dx. And then this is easy to do because all we have to do is the sum. So this would equal x to the 4 over 4 for this first case. And then the other one is going to be x to the 3 over 3. And then we just write plus c, representing a possible constant. Next we have example 11.3. And it says evaluate a, the integration of t cubed minus 3t to the 5 over t to the 5 dt. So this is a case where we can separate this into two different integrals, right? Notice that we can rewrite this as the integration of t cubed over t to the 5. And this minus the integral of 3 t to the 5 over t to the 5 dt. And now we can just use basic algebra to simplify this, and we're going to get that this is the same as the integral of t to the minus 2 dt and minus, and this will cancel out here, so we're just going to get 3 dt. So notice that this is now easy to integrate because all we have to do in the first case is add 1 to the exponent. So we're going to get t to the minus 1 divided by minus 1. And here we're going to get simply minus 3t, which is the antiderivative of 3 in terms of t. And let's not forget plus c. But obviously we can rewrite this as negative 1 over t minus 3t plus c. So now let's do b. So for b, we have to evaluate the integral of x plus 5x to the 4 over x squared dx. So notice that this is very similar to the previous case because we can separate this into the integral of x over x squared dx plus the integral of 5x to the 4 over x squared dx. And then from here, we're going to get that this is equal to the integral of 1 over x dx plus 5, because it's a constant, so we can pass it through the integral symbol. So 5 times the integral of x squared dx. So now we're ready to integrate this because it's pretty straightforward. So if you have the integral of 1 over x dx, the solution to that is going to be natural logarithm of the absolute value of x. So notice that if you have the natural logarithm of x, the derivative of that is 1 over x. Therefore, the antiderivative of 1 over x is going to be natural logarithm of absolute value of x. And why absolute value? Because remember that you cannot solve for a negative natural logarithm or any logarithm. Okay, so then this plus 5, and here we apply the power rule, adding 1 to the exponent and dividing by that same number. So 5 times x to the 3 over 3, and let's not forget plus c. So next we're going to take a look at integration by simple substitution, or also known as change of variables. First of all, let's suppose you have a function y is equal to f of g of x. So how do we do the derivative of this? Well, remember that we would have to apply the chain rule. So to do the chain rule, remember that we do the derivative of the outside function, leaving the inside function intact. And we multiply that times the derivative of the inside function. So this is the chain rule. So notice that if we have this situation here, we could do the inverse and find the antiderivative very easily. So notice that we would have to have a situation where we have something like, to put it in simpler words, let's suppose we have derivative of f of u times the derivative of u. So if you have this situation where you have a u and then the derivative of u, we can integrate this, for instance, and get the original function. So that's what we're going to do here. We're going to use a substitution or a change of variables. Normally, we do it using the variable u, but it's not limited to u, obviously. Okay, so let's start with letter A. Okay, so for letter A, they want us to evaluate the integral x cubed plus 2 to the power of 10 times 3x squared dx. So notice that if you wanted to do this directly, it would be very complicated because you would have to expand this expression here to the power of 10 and then multiply it by this and then just do the power rule. But that would take a long time. It's much easier to think about the situation where we can do substitution. So what do you have to look for here? The first thing is, what are you going to call u? Now, the easiest thing to substitute is going to be this expression inside here. We can call this u. So if u is x cubed plus 2, then the derivative of u, because we're doing it in terms of u, it would have to be 3x squared times the derivative of x, right? So notice that we have everything necessary to substitute because this expression here is the same as this one. So we can rewrite this integral as the integration of u to the power of 10 du. And this is a very simple integral to solve because this is simply going to be u to the 11 over 11 plus c. But they didn't ask us to solve this in terms of u, so we have to substitute back. So this is going to equal x cubed plus 2 to the power of 11 over 11 plus c. So for b, they want us to integrate tangent of x dx. So notice that we don't have an antiderivative for tangent. We know that the derivative of tangent is secant squared, but the antiderivative of tangent is not secant squared. So we need to do a simple substitution. So how can we do that? Well, if we say u is equal to tangent of x, we don't have secant squared of x. So we're going to have to express tangent in terms of sine and cosine. So notice that this is the same as saying sine of x over cosine of x dx. So now we have to choose u and derivative of u. So in this case, notice that we can rewrite this as, notice that this is the same as saying 1 over cosine of x times sine of x dx. So let's attempt to do u substitution. So if we say u is equal to cosine of x, the derivative of u would be negative sine of x dx. So notice that we're missing the negative sign here, right? This negative sign that we need is not present in the original integral, but we can just put it here, right? We can just say that this is minus sine of x. Now, of course, we would also have to put a minus in front of the integral in order to not change its value. So now we're ready for u substitution, because this is the same as saying negative integration of 1 over u times the derivative of u. And if you recall, this is simply going to be negative natural logarithm of the absolute value of u plus c. Substitute back, and this is going to be negative natural logarithm of cosine of x plus c. And then because we can send this as an exponent here, right? Remember that from natural logarithms or logarithms in general? We're going to get that this is the natural logarithm of secant of x plus c. So for c, they want us to find the integral or evaluate the integral of cosine of 5x dx. So let's do the u substitution. Now, if we say that u is equal to cosine of 5x, notice that the derivative of this, the derivative of u, would have to be negative sine of 5x times 5. So we don't really have this, well, dx, don't forget that. So we don't have this. So in these cases, what I recommend is that you take this part, make this u. So if you go, all right, let's make u, instead of cosine of 5x, let's make u simply 5x. So then what is the derivative of 5x? What is the derivative of u in this case? Well, it's going to be 5 dx. So there's a problem because we don't have 5 dx, we simply have dx. But we can do what we've done before. We can simply put a 5 here to get 5 dx, and then we would have to eliminate that 5 by multiplying by 1/5, which is the same as dividing by 5, right? So then now we're ready for the u substitution, because this is simply going to be equal to 1/5 the integral of cosine of u du. So this is very straightforward because we know that the antiderivative of cosine is simply going to be sine. So the solution to this is going to be 1/5 sine of u plus c. But we have to plug in back u, right? So this is going to be finally 1/5 sine of 5x plus c. So letter D is very similar. They ask us to evaluate the integral of cosine of x squared times x dx. Now be careful because this is inside the cosine function. This is not, right? So let's say that u is equal to x squared. Therefore, derivative of u would be 2x dx. So we don't have the 2, right? We don't have it here. So just let's do what we did before. Let's put a 2 here and multiply by 1/2. And now we're ready for u substitution. So this is going to be 1/2 the integral of cosine of u, and this is du, derivative of u. So now once we have that, it's easy to integrate because this is simply going to be sine of u plus c, sine of x squared plus c. So for e, we have to evaluate the integral of Euler's number to the power of 3x plus 1 dx. So whenever you see Euler's number, do the substitution with the exponent. So you would say, all right, so u is equal to 3x plus 1, therefore the derivative of u is going to equal 3 dx. And then again, we don't have the 3, but we can put it here and just multiply by 1/3, and that won't alter the value of the integral. So let's do u substitution. We have 1/3 the integral of e to the u du, and this is simply 1/3 e to the u plus c. Plug in whatever u was, so this is going to be then 1/3 e to the power of 3x plus 1 plus c. Very well, so now we are in example 11.5, and it's a very similar example where they ask us to evaluate each integral, and we're going to have to use u substitution. So letter A is very similar to the previous one we did, and it's the integration of Euler's number to the power of minus 3x dx. So we say, okay, let's make u negative 3x, therefore derivative of u is going to be negative 3 dx. Again, we don't have negative 3 dx, so we're going to have to add negative 3 here, or just put it there, negative 3, and then divide by negative 1/3. Do the u substitution, negative 1/3, the integral of e to the power of u du, and this is simply going to be negative 1/3, negative 1/3 e to the u plus c. We plug back in, and negative 1/3 e to the minus 3x plus c. For b, we have that they want us to do the integration of sine squared of x times cosine of x dx. So in these cases where you have sine and cosine, you have to pick which one is going to be u and which one is going to be the derivative of u. Notice that this one is to the power of 2. So because this one is to the power of 2, you're going to want to make this one your u. So u would be sine of x. And the derivative of u is going to be cosine of x dx. So notice that we're all set up to do the substitution. So this is going to be the same as the integration of u squared du. And this is very easy because it's simply going to be u to the 3 divided by 3 plus c. But we need to substitute back in. So this is going to be sine cubed of x over 3 plus c. So for c, they want us to evaluate 2 times sine of 3x minus 5 dx. So notice that we can't do the u substitution, u equals sine of x, right? That wouldn't make sense because we don't have cosine of x and all that. But we can take this. So if we say that u is equal to 3x minus 5, then derivative of u has to be 3 times dx. Okay. So let's rewrite this here as 2 times the integral of sine of 3x minus 5 dx. Again, the derivative of u is 3 times dx, so I need to multiply here by 3, therefore also divide by 3. So notice that we're ready because this is simply going to be, that is going to equal 2/3 the integral of sine of u du. And then the antiderivative of sine, remember that you have to be careful because that's going to be negative cosine, right? So negative 2/3 cosine of u plus c. And then just plug back in whatever u was, right? So this is just simply going to be negative 2/3 cosine of 3x minus 5 plus c. D is basically a general rule for Euler's number. So notice that if you have the integral e to the power of mx plus n dx, notice that if you want to do u substitution, you're going to say, well, u is equal to mx plus n. Now don't worry about m and n because m and n are simply constants. Then treat them as such. So you know that the derivative of u is going to be m dx, all right? So we don't have m, therefore we need to put an m here and then divide by m or multiply by 1 over m. And we can do the substitution. So 1 over m times the integral of e to the u du, and this is simply going to be 1 over m times e to the u plus c, but we said that u is mx plus n. So then we get 1 over m times e to the power of mx plus n plus c. So this is a general rule for the integration of Euler's number with an exponent that is linear. So you have to be careful, right? It only applies to the cases where the exponent for Euler's number is linear. Okay, so finally we'll do e, and they want us to integrate x times the square root of x dx. And they tell us that when you plug 1 into the antiderivative, you get 2. So what this implies is that we can find c. So we don't have to write this in terms of c, but actually we will have an actual constant. Now this is useful later on when we see cases with velocity and acceleration and distance and so forth. Anyway, so will we do u substitution here? Well, before you ever do u substitution, be careful because sometimes you don't need to use it. Notice that this is the same as saying the integration of x times x to the 1/2 dx. And remember that this is the same as x to the power of 3/2, right? We add the exponents. So 3/2 dx. And then this is a simple integration where all we have to do is apply the power rule, right? So all we have to do is add 1 to the exponent and divide by that number. So we're going to get x to the power of 5/2 divided by 5/2 plus c. And then this is equal to 2/5 times x to the power of 5/2 plus c. But recall that they told us that when you plug in 1 into the antiderivative, you get 2. So with this, we can find what c is, right? So let's say 2/5 times 1 to the power of 5/2 plus c is equal to 2. So that just simply means that c is equal to 2 minus 2/5. And if you do the math, c is going to equal 8/5. Therefore, that means that we have a solution for this, including the constant, which is 8 over 5. Okay, so now this is example 11.6, which will be the last one on this video. Evaluate each integral. So for a, they want us to evaluate the square root of 6x plus 11 dx. So let's simply say that u is equal to 6x plus 11. Therefore, the derivative of u is going to be 6 dx. So we don't have the 6. We will have to put the 6 here and then multiply by 1 over 6. And we're ready to do the substitution because then this will equal 1/6 integral of u, square root of u, but I'm just going to say u to the 1/2 du. And then this is easy to do because we know that this is going to equal 1/6 times u to the power. In this case, if we add 1, remember that we're going to get 3/2. But also we have to divide by 3/2. But that's the same as multiplying by 2/3, right? Dividing by 3/2 is the same as multiplying by 2/3, and then plus c. And this is going to equal 1/9 times u to the power of 3/2 plus c. And don't forget to plug in whatever we had for u. So final solution, 1/9 parenthesis 6x plus 11 to the power of 3/2 plus c. For b, we have the integration of 5x cubed plus 2, and all this to the power of 8 times x squared dx. So again, let's make u into 5x cubed plus 2. Therefore, the derivative of u is going to be 15x squared dx. So we have the x squared, but we don't have the 15. So that means that, again, multiply here by 15, and then here divide by 15. And we're ready to do the u substitution. So then this is going to be the same as 1/15 times the integral of u to the 8 du. And then again, simply use the power rule here. So it's going to be 1/15 times u to the 9/9 plus c. And this is going to equal 15 times 9 is going to be 135. So 1/135 u to the 9 plus c, and then substitute back for u. So it's going to be 1/135, and we said that u is 5x cubed plus 2. Don't forget the exponent to the power of 9 plus a constant c. So for letter C, we have the integration of x cubed minus 2 over the cubic root. Is it the cubic? No, it's the fifth root. So it's the fifth root of x to the 4 minus 8x plus 13 dx. So here, always pick u. Choose the u that is caught in an exponent, right, or caught in a root. So u would be x to the 4 minus 8x plus 13. Therefore, the derivative of u would be 4x cubed minus 8 dx. So we need this in order to be able to do the u substitution. So notice that we don't have it. But what happens if I multiply this here by 4? Well, I will get the same expression, right? 4x cubed minus 8. But I can't just do that without dividing by 4 or multiplying by 1/4. So there we are. Now we're ready to do the u substitution. So this is going to be the same as saying 1/4 the integral of du over, and yeah, let's just do it step by step. So this over u to the 1/5. U to the 1/5. But notice that this is the same as saying 1/4 the integral of u to the negative 1/5 du. And this is very straightforward for integration because this is simply going to be adding 1 to the exponent again, right? And this is going to equal 1/4 times u to the power of 4/5 divided by 4/5, or which is the same, multiplied by 5/4. And this plus c. So then if we multiply that, we're going to get 5/16, and u to the 4/5 plus c, and then we substitute back in, and we're going to get 5/16 times x to the 4 minus 8x plus 13 to the power of 4/5 plus c. And then finally, for D, they want us to evaluate the integral of sine to the 4 of 3x squared times cosine of 3x squared times x dx. So whenever we do use substitution, we want to choose whatever expression is to a power or stuck in a root, right? So in this case, let's do u is equal to sine of 3x squared. Therefore, du, or derivative of u, is going to be cosine of 3x squared times 6x dx. Okay, so notice that this we do have, right? It's right here, sine of 3x squared to the power of 4. But we are not complete here. We're missing a 6. So that means that we have to put a 6 here to multiply. Therefore, divide by 6 or multiply by 1/6. So now we're ready to do the u substitution because this is going to equal 1/6 the integral of u to the 4 du. And then this is nice and straightforward. It's just going to be 1/6 times u to the 5/5 plus c, which is the same as 1/30 u to the 5 plus c. Then all we have to do is plug back in for u. And then we said that u is sine of 3x squared. Therefore, this is going to equal, and the solution will be 1/30 sine to the power of 5 of 3x squared plus c.